Good evening, this is MP Live Lessons, and we are back tonight, and we are revising Physics Paper 2 with forces. One of the 3 units, but we're going over 2 tonight. The first thing we need to get clear with is the 2 words that are fundamental with forces. So we have the terms scalar and vector. These often refer to quantities, used a lot in physics and maybe maths as well. For example, speed is a scalar quantity, but velocity is a vector quantity. By scalar quantity, we only mean it just has a magnitude, meaning a size, a number. For example, in this case of speed, we could say something like 50 miles an hour. Whereas vectors, they have a magnitude
Wait, I'll be back in a second.
and a quantity. So you'd, for example, here, you could say also 50 miles an hour, but give the direction. You could say to the north. Some other examples of scalar and vector quantities could be, for scalar, distance, while for vectors there could be displacement. And a good thing to know as well that a vector quantity is also forces, the whole of this topic. So when you're asked to give a force, you could be asked as well to give the direction of it. Usually you can say descriptively, like to the left, right, up or down. Sometimes it can be at an angle. Now we've got a few types of forces. There can be a contact force or a non-contact force. As the name suggests, contact forces, 2 objects have to be in contact with each other for this force to happen. Examples of this could be friction. It could be like an object on the surface that resists the motion. Another one could be air resistance or drag. And lastly, many push or pull forces are contact forces. Some examples of them could be tension in a string, as well as, let's say, contact forces such as yeah, and then thrust as well. Some non-contact forces, as the name suggests, do not need objects to be touching with each other, and these often use or involve fields of some kind. This could be magnetic fields, so magnetism is a non-contact force. And one good example that we'll look at constantly is, well, gravitational pull. This can be also called weight, which we'll come into in a bit. The next thing we're going to look at now is the concept of weight. And I'd like to get that down as a title. This is important. Weight is a force caused by gravity. And the thing is, weight and mass are not the same thing. After all, mass is actually the content and size of you. You could be 30 kilograms on Earth, and if you move to the moon, you're also still 30 kilograms, but your weight will be different. This is because weight depends on your mass times your gravitational field strength of the object you're standing on. For on Earth, this is about 9.8 or 10. So they'll give you this in the exam. Since weight is a force, it is measured in newtons and can be measured by things like a Newton meter. Mass will be measured in kilograms, and the gravitational field strength is measured in newtons per kilogram. For example, an object weighing 10 kilograms has a weight equal to its mass, which is 10 kilograms, times the gravitational field strength, which is about 9.8. So its weight is about 98 newtons. Next after this, we will look at interacting forces. So imagine an object on a surface, like a table. I'm going to use just a simple box for this example. Can you think of the forces that are interacting on this box? First, there could be weight, which is what we talked about, which I'll label with a W. And remember to draw these forces as arrows, pointing in your specific direction, and just remember as well that its length or size literally can represent how much it is unless you label it. However, if the box is still, weight isn't the only thing that's interacting on the box. If weight was the only thing interacting, it would pull it straight down through the table and this wouldn't make sense. Therefore, you need to have an opposite equal force called the reaction force. Have you ever noticed with yourself, for example, if you push down on something like a wall or down on the table, you can almost feel as if the table pushes back or the wall pushes back. This is actually the reaction force. If we start to move our box, let's say to the right with the pushing force, I'll label with P, this will give us some friction that opposes this motion. This can be a good example of a free body diagram. And next thing you could look at are resultant forces. And these are the overall force acting on an object. If we ignore all the others, I'll show what I mean. So suppose our weight force, I'll label it now as about 498 newtons. Our reaction force will be also 98 newtons. Now suppose our pushing force, could be 60 newtons, whereas our frictional force could be 20 newtons. When we have two opposing forces, such as here and here, we subtract them. Um,
Who prepared the table? It was there on the table while I was working.
Was in that bag.
Huh?
Was in that laptop bag.
Where is it?
It used to be here, but right. So we had some problems there for a bit. So as I was saying, if we have forces acting against each other, like the highlighted ones, we take them away. So the resultant force is 60 minus 40, minus 20 actually, which gives us 40 newtons. And remember that forces are actually a vector quantity, so you have to give their direction. So 40 newtons to the right. So we can draw this box again with a single resultant force of 40 newtons to the right. Sometimes you might be asked to calculate the acceleration of this object based on its force and mass. There's a formula to work this out, which is acceleration equals the force divided by its mass. Sometimes you might be asked to rearrange this formula. In this case, the acceleration of this box will be 40 divided by 10, which gives us 4. And the units for acceleration are going to be meters per second squared. Next, we're going to look at springs, which we have not seen for a while. To briefly recap,
What was that just equation? Was that like force divided by mass equals acceleration?
Next time.
acceleration is force divided by mass.
Yeah.
Was it? Did you find it? Why did you put it? So let's say we have a spring right here, and we'll just loop this around. So the spring has its initial length. Now when we attach a force to it by pulling on it, let's say with the weight, it will extend.
Did you bring when you brought your laptop upstairs? Was there a notebook upstairs? Downstairs.
I didn't see one downstairs.
So what? It disappeared on its own.
Just wait for a bit, I'll have to deal with something. So is everyone still there? Had to sort something out. Great, you're still there.
Yeah. Yeah.
Okay, good. So as I said, if we attach a mass to a spring, the spring will extend, and this is your extension. Now there's also another formula for this. I think you'll be given this again. Now the force is proportional to its extension, so there's some number involved, and this is called the spring constant. And it's different for every spring. So if we have the units as well, the force in newtons is equal to the spring constant, newtons per meter, times the extension in meters. Typically, you will never get the spring extending in meters. It will only extend down by a few centimeters sometimes. As an example, a force of about, let's say, 2 newtons extends a spring, it's by 10 centimeters. So we'd plug this into our formula, remembering what our units are. So our force in 2 equals the spring constant times our extension, which is 0.1. So our spring constant equals 2 divided by 0.1, which gives us 20 newtons per meter. This is a simple calculation. You might be asked to do a practical on this as well. In this case, you'd attach first see the length of the spring with no mass. Then you'd start adding regular amounts of mass or weight. Let's say about 1 newton every time. And then you'd at each time that you add a mass, record the extension of the spring. And as a reminder, the extension of the spring equals its length now. Take away its original length, the one that you measured at the start. And to measure this, you will often use little clamps setup. You could have a clamp like this, like a little crab claw. And then you'd have the spring attached. And you'd also have a ruler hanging down, probably by a little attachment here. And then you just mark out with your eye how long the spring is. But this could actually be a source of random error. This is because your measurements could be too high or too low. And just remember, let's say these are your eyes right here. They need to be in line with what you're measuring to the ruler, not above and not below either. And what you'll get is little graph as well. If you plot force on the x-axis and the extension on the y-axis, you'll literally get a line that shows it's directly proportional. So it means as it doubles, as the force doubles, the extension will also double. However, if you keep adding so many masses on, the spring will eventually deform permanently and it won't change to its original length. And you can tell it's gone past if you see the line starts to turn into a curve that goes upwards like this. And this point here where it starts to go up is called the limit of proportionality because it stops being directly proportional anymore. So I'll let you get these notes down and then we'll move on to the next bits of forces. Another neat thing about this graph as well, it can be used to calculate the spring constant. The spring constant in newtons per meter is also the gradient, but in this case you'll have to do it the other way around. So if you were to find the gradient here, you do the change in y by the change in x, but this gives us the extension per force, and yeah, that's the wrong way around. So what you do is, if it's this one here, you take the gradient and put into your calculator just to the power of -1. This gives you the spring constant. Now be aware, in questions, they can give you graphs with the axes with other labels as well. They might put the force here on the y-axis, and then the extension on the x-axis. So what I'm saying is these axes may not be the same. They might be switched around. So in that case, instead of the line eventually curving up, instead you'll get the line start to curve and start to flatten a bit. But the same limit of proportionality is when that line just about stops and then starts to curve. That's the limit of proportionality. It's still the same thing. Now we'll move on to some graphs this time. One of the graphs you'll be assessed on are known as speed time graphs, or actually distance times graphs. First we'll go over distance times graphs. let's sketch something right here. So we got a distance. This can be sometimes called a displacement. And we got time on here. Suppose I'm a cyclist and I take a little journey away from home on a nice sunny day. So at first, when I leave home, this can be shown by straight lines, so I'm traveling at a constant speed away from home. If then the line starts to flatten like this shows I'm taking a rest. When I go um, cycling again, this will be shown by another line, but if I go a bit more shallower, like this, it shows I'm at a slower speed. So in a distance time graph, the gradient is your speed or velocity. And then finally, you'll sometimes see the line coming back down, which means I'm traveling home. Sometimes the line could curve, so if I draw a new graph, and what's going on? Okay, so rub this out. And the whiteboard lags once again. So if I draw a new graph this time, and I show, let's say, a line is curving up like this, and this means the gradient is getting much steeper and steeper, so this actually shows acceleration. Whereas let's say if it starts to flatten out, the gradient becomes more shallow and shallow. This means it's decelerating. The next kind of graph you could look at are velocity time graphs. As the name suggests, on the y-axis, it will measure velocity, or how fast something is, and the x-axis, it's still time. Now this is very different to a speed time graph, and make sure you always read the question. If we've got a straight line, this time it shows acceleration because your velocity is changing and it's increasing. So any line that goes up is just acceleration. If we've got a flat line, this means the object is traveling at a constant velocity. And then now, if we've got a line going down, the velocity is decreasing, so it's decelerating. You might have learnt this in maths as well. Another thing to know is that the area under this graph, which I'm highlighting now, is equal to the distance covered. One thing they will tell you to do with these graphs is to calculate acceleration from plotting some points. They could do this or ask you to do this in a few ways. One, they could tell you to plot between 2 points. This is actually the easiest of them. For example, you could have a curve like this, and then it will ask you to find the acceleration between this point and this point, and you'll simply draw a line here, and then you can draw your own triangle like this to find the gradient. So this is the change in y, and this will be your change in x. Don't forget as well to read off your values to the axis. And do this with a straight line and make sure you know the scale. Another thing they could ask you to do is to find the acceleration at a certain point. So if I draw a curve again, they might tell you to find the acceleration or the gradient at this point. In this case, you will instead draw a tangent. So it will just touch the curve at this point and nothing where else. And you can keep drawing this line and draw a triangle how big you like to once again find the gradient, the change in y divided by the change in x. For your information as well, everyone's tangents will be different, so there is a tolerance for answers. For example, they'll allow a value between, let's say, 0.9 or 1.2, something like that. So I'll let you get these notes down and then we'll look at terminal velocity. So let's say I'm going to draw a plane right now, just a very baddish plane. Which looks a bit more like a whale. Now, if someone were to jump out of this plane, how could you describe their motion? So when they first jump out the plane, if we label the forces, they've got their weight pulling them down. And at this point, acceleration is at its highest. Now, as they start to fall down, they'll start to pick up speed. So as speed increases, air resistance increases. That's their drag. That's them passing through the Earth's atmosphere. And it's like good to know as well, that their acceleration decreases. This continues to the point where they're very scared because now they've reached something called terminal velocity. Because this is when their weight is equal to the air resistance. So when we remember to resolve forces or to find the resultant force, we will take away these. So overall force here now is 0 newtons. So they aren't accelerating anymore. So they are falling at a constant, hence terminal velocity. Now, since they're scared, they'll then want to deploy the parachute. What happens this time is that the air resistance will increase dramatically already. So since the resultant force is going this way, which I'll draw in blue, they will start to decelerate. In other words, slow down. Once again, since the speed decreases now, the air resistance will also decrease. This comes to a point where, once again, since the air resistance will decrease and decrease again, the forces are balanced again. So the overall force is 0 newtons, no acceleration anymore, or change in velocity, and they've reached a new, slower terminal velocity. And hopefully at this point, a little guy here has reached back to the ground. Now this is important because this could be quite a high mark question. This could be about anywhere from 4 to even 6 mark explanation. And you'll need to remember each of these stages to get as many marks as you can. The last thing we'll look at now is momentum. So momentum is based on an object moving. So momentum equals mass times velocity. So we know the units for mass and velocity. So mass is measured in kilograms and velocity in meters per second. So therefore our momentum will be kilograms meters per second. So combining those units together. So this kind of describes how much oomph something has if you were to collide with them, perhaps. In many of the questions, you'll be given two objects that interact with the momentum. Suppose we have a snooker ball, the white one that gets hit. Now let's say it's going to hit this red ball. And this red ball isn't moving, actually. And let's say this snooker ball is moving here to the right at 1.5 meters per second. And let's say each of these snooker balls have a mass of, let's say, 250 grams, or 0.25 kilograms, which is quite heavy still. So we'll calculate the momentum of those first. The first one is obvious, with the snooker ball being still, it has no velocity, so its momentum is simply 0 kilograms meters per second. The white snooker ball, we can see these mass and velocity, so we simply multiply them together. And we'll get, if I'm right, 0.375 kilograms meters per second. Now, when these two balls collide, some things can happen. And you don't need to know what outcome there would be. For example, if they carry on together, one goes faster than the other, or they go back. The key thing here is to understand that the momentum before here is equal to the momentum after. So that's the total. So suppose, let's say, this snooker ball will collide with the red one, and they'll just move together. If this happens in a question, you would basically treat this as one very big object. So now they'll have a combined mass of half a kilo, 0.5 kilograms. They will still move with the velocity, and we'll calculate that. And the total momentum remains the same, which is 0.375 kilograms meters per second. Now if we do a bit of maths, we can calculate the velocity by having the momentum divided by the mass. So this would be equal to 0.375 divided by 0.5. This would get, if I'm right, 0.75 meters per second. So that's their speed. But don't forget the direction as well. So 0.75 meters per second to the right. That's just one example of a momentum question. This can also explain other things. For example, if you're stood in an ice rink and you have an object on you like a bag and you're standing still, but if you throw that bag away, you will appear to move backwards. This is also due to the conservation of momentum, because your momentum before is 0 and your momentum after is still 0 in total, but momentum is also a vector quantity and they'll act in opposite ways, just like resolving forces. The last thing we're going to look at now are some vector diagrams. And this is the last bit for today on forces, before we move on to waves. Now with the vector diagrams, you could be given two forces, for example, on an object. Let's say we have our box again, and we have a force acting this way and this way. Now, if we could to combine these forces into one single resultant force, we would actually expect this to be diagonal. What we can do is accurately draw a little triangle here that connects the two to form a little right-angled triangle. So let's say this upward force is 4 newtons, and this rightward force is going to be 6 newtons. Now we've got a triangle here, we can actually do some maths. And we can, let's say, use Pythagoras, or another method which I'll explain in a bit. So if we've got 6 here and 4 here, this resultant force going in this direction, which I'll draw in blue, is equal to 4 squared plus 6 squared. Let's just say it's the square root of 52 newtons. And you would use a calculator in an exam to work this out. Your alternative method is to measure. So the thing is, on these vector diagrams, they might give you a little scale on the side. This could be, let's say, 1 centimeter, which could equal some number of newtons, let's say 2 newtons. And what you'd do is you'd still draw the same triangle, but you'd instead use your ruler and measure right here. As I've said many times throughout this lesson, forces have a magnitude, like this, as well as a direction. If you're comfortable and confident with maths, you could use a bit of trigonometry to find this angle however you like. Or, if you don't want to, you should absolutely use a protractor. And this is a reminder as well, for Physics Paper 2, you should bring a protractor with you in case these kinds of questions come up in the exam.
Matthew,
Yep.
will we also get like a sheet telling us all the equations or not?
Yes, we'll be given a sheet with all the physics equations on.
Ah, thanks.
So that's almost it for vector diagrams, because they could ask you to do the reverse. They might give you a resultant force, let's say 9 newtons, and give you the angle, let's say at 50 degrees. And you might actually need to do something called resolving this force. In this case, you do the opposite. You'll find the triangle again, to find its horizontal bit and its vertical bit. And this will give you its horizontal force and its vertical force. And again, you can accurately do it by Pythagoras or trigonometry, or you can use your scale diagram like this to figure the components out again. So just a reminder for these vector diagrams, I should absolutely recommend bring a protractor and a ruler. It may help. So that's actually it for the first part of this evening revision. That is forces done for you. And next, in about 2 to 5 minutes, I will do waves, which you've been recently doing.